For decades, the world's most infamous tractors didn't just break new ground, they broke the very rules of safety and sanity we take for granted. Some weighed more than a dozen cars, twisting steel frames just to pull harder. Others sounded like thunder, but ran so hot they threatened to melt down mid-harvest. These weren't prototypes or black market machines, they were sold as everyday farm tools, trusted by families who never realized what hidden dangers lurked inside. If a single overlooked detail could turn a reliable workhorse into a walking disaster, how many close calls went untold? Let's count down the 10 tractors so dangerous you'll wonder how they ever made it into the field. In 1978, a hulking machine rolled out of a modest Australian workshop and onto the wheat fields of New South Wales. The nameplate read Upton HT14 350, but nothing else about it was modest. Weighing in at over 25 tons, the Upton dwarfed nearly every tractor before it. Its two-wheel drive was simple, but the sheer mass pressed its tires deep into the earth, delivering traction that seemed unstoppable on heavy stubble soils. For a moment, it looked like brute force had finally conquered the Australian outback. But the ground beneath told a different story. University soil studies, published in the years after the Upton's debut, revealed a problem no one had anticipated. With each pass, the massive axle load crushed the subsoil, squeezing out air and water. Farmers who had once cheered the Upton's power soon found their fields scarred by permanent ruts and plagued by waterlogging. Yields dropped, and some patches never recovered. Extension bulletins warned that compaction from tractors over 11 tons per axle could cut crop production for years. The Upton, at more than double that threshold, left a mark that lingered long after the engine cooled. Moving such a giant was another trial. Getting the Upton from farm to farm meant special permits, closed roads, and sometimes even rail transport. Its size, once a symbol of ambition, became a logistical headache. Australian regulators took note, and new rules on field weight and transport followed soon after. In the end, only a handful of Uptons ever worked the land, but their legacy survives in the cautionary diagrams and soil cross-sections used in agricultural colleges to this day. Half a world away and a few years later, another kind of power race was underway. In the early 1980s, John Deere engineers took a leap, swapping their trusted 6-cylinder engines for a massive V8 in the 8850. The sound alone was enough to turn heads at farm shows, a deep, rolling thunder that promised to pull bigger implements and cover more ground than ever before. On paper, the 8850's 300-plus horsepower looked unbeatable, but the V8 came with a hidden price. The engine ran hot, pushing the limits of its own cooling system. At the 1983 Farm Progress Show, the 8850's engine overheated in front of a crowd, forcing operators to tow it off the field. The embarrassment rippled through the industry. Farmers who bought the V8 found themselves facing high fuel bills and, when trouble struck, a maintenance nightmare. Servicing the engine meant splitting the tractor in half, a job that could sideline a machine for days and drain a repair budget in a single stroke. By the end of the decade, the 8850's V8 was gone, replaced by more reliable inline engines. Restoration mechanics still talk about the 8850 with a mix of AWE and dread. It was a machine that chased power to the very edge and sometimes right over it. From the Upton's crushing weight to the Deere's overheated promise, the early years of the horsepower arms race proved that more is not always better. Sometimes it is just heavier, hotter, and a lot harder to live with. In the years after World War II, British farmyards became workshops of invention. The Fordson E27N, a plain but dependable tractor, found its way into the hands of tinkerers who wanted more power than its designers ever imagined. With surplus engines available and welding skills in abundance, some farmers took the bold step of bolting 2 engines onto a single Fordson frame. The hope was simple: double the horsepower, double the productivity. But the reality was far less forgiving. The original chassis, never meant to handle that much torque, began to twist under the strain. Oral histories from the 1950s recall frames cracking wide open in the middle of a field, leaving operators stranded and repairs stretching on for weeks. Driveline synchronization became a daily battle. Keeping two engines running in harmony was nearly impossible with the crude linkages and controls of the era. Operators described the experience as chasing ghosts. One engine would surge, the other would lag, and the whole machine would lurch unpredictably. Some conversions ended with a loud bang and a torn frame, a lesson in the limits of homegrown engineering. Meanwhile, a different kind of risk crossed borders from the east. The Belarus MTZ80, produced in the Soviet Union, arrived on Western farms in the late 1970s and early 1980s as a bargain alternative during tough economic times. These tractors were praised for their rugged simplicity and low price, making them a lifeline for farmers with tight budgets. But the cost savings came with hidden dangers. The MTZ80's hydraulic system lacked a pressure relief valve. When pressure built up during heavy use, hoses could burst without warning, sending hot fluids spraying across the operator's workspace. In 1982, after a series of burst hose incidents, Poland's agricultural ministry and East German importers temporarily halted deliveries until a fix could be found. Field repairs became a routine part of ownership, and stories spread of farmers carrying spare hoses and wrenches just to finish a day's work. Electrical quirks added to the unpredictability. Instead of a dedicated ground wire, the MTZ80 used the tractor's steel frame as the main electrical path. This shortcut led to erratic starting, flickering lights, and in some cases mysterious shorts that left mechanics scratching their heads. For many, the Belarus was both a blessing and a gamble, a machine that could take a beating but demanded caution and constant attention. Both the Fordson twin-engine experiments and the Belarus MTZ80 highlight a recurring theme in tractor history: the drive to stretch a machine's limits, whether through grassroots ingenuity or factory shortcuts. Sometimes, the result was a leap forward. Other times, it was a hard lesson in the cost of pushing too far or cutting too many corners. On paper, the Massey Ferguson 135 looked like the answer to every small farm's needs. Compact, easy to maneuver, and built to last, it became a fixture from the rolling hills of Appalachia to the valleys of Wales. By the mid-1970s, the MF135 was everywhere, pulling hay balers, hauling trailers, and working slopes that older, heavier machines could not reach. But hidden in that nimble frame was a risk no one expected. The very geometry that made it so versatile also made it dangerously unstable on uneven ground. The MF135's short wheelbase, just about 6 feet from axle to axle, meant it could turn tightly and slip between rows with ease. Yet when a heavy implement was hitched to the rear or a round bale lifted high, the tractor's balance shifted in ways that were not obvious until it was too late. Studies from university extension programs in the 1970s measured the tipping point. The MF135 would pitch over at a lower slope angle than its longer, heavier rivals. On a side hill, or when crossing a ditch, the front wheels could lift suddenly, and the whole machine might roll before the operator had time to react. These were not isolated incidents. National safety surveys from the era linked the MF135 and similar models to a disproportionate number of rollovers and serious injuries. One case from 1974 brought the problem into sharp focus. In the hills of eastern Kentucky, farmer Clyde "Red" Jameson was baling hay when his 135 slid sideways on a damp slope. Jameson later told a local paper from his hospital bed, his leg in a cast, that it slid sideways, then just went over like it was nothing, and that he never saw it coming. His story echoed through farming communities. Operators who had trusted their tractors found themselves caught off guard by a flaw they never imagined. Accident records from the 1970s and early 1980s show tractor rollovers killed more than 100 operators per year in the United States alone. The MF135, with its short wheelbase and rear heavy loads, appeared again and again in the case files. The pattern was clear. Even experienced drivers could be caught out by a sudden shift in weight or a hidden rut on a hillside. Safety researchers and extension agents began to push back against the idea that rollovers were just the price of farm work. They pointed to the MF135 as a textbook case, a machine where power and utility outpaced the geometry needed for stability. Their advocacy helped launch the first campaigns for rollover protective structures, usually called ROPS, in both the UK and the US. Regulators and manufacturers took note. By the late 1970s, the MF135 and its peers became the poster children for ROPS retrofit programs, and safety training started to include real-world lessons drawn from these accidents. Today, the MF135 story is a reminder that even the most reliable machine can hide a blind spot. It is not about blaming the tractor or the operator, but about understanding how design decisions like a short wheelbase can tip the balance between safety and disaster. The lessons learned from the MF135's instability did not just change one model. They reshaped the way the world thinks about agricultural safety. The early 1970s saw International Harvester roll out the 1066, a tractor that captured attention with its enclosed, weather-tight cab. The cab felt like a leap forward, promising comfort and protection for operators facing long days in the field. It shielded drivers from dust, rain, and the relentless sun. But the design held a flaw no one caught until machines were already working across the Midwest. The intake for the cab ventilation system sat just feet from the exhaust outlet. On calm days, when the wind died down, exhaust fumes drifted directly into the operator space. Farmers began noticing headaches and fatigue after hours behind the wheel. Some described a metallic taste at the back of the throat, others reported a lingering drowsiness that did not make sense. Complaints trickled into dealerships, and engineers at International Harvester studied airflow diagrams, trying to trace the invisible path of exhaust into the cab. Lawsuits and medical reports followed, and the 1066's cab intake placement became a cautionary example in farm safety courses. By the mid-1970s, the company issued service bulletins warning of the fume risk and advising cab modifications or retrofits. Later models moved the intake to safer locations, and the lesson became part of engineering curricula. Comfort features can backfire if airflow is not fully understood. A generation earlier, Allis-Chalmers faced a different problem with the WD45. Introduced in 1953, the WD45 was a powerhouse for its time, boasting live hydraulics and a reputation for reliability. But the original brake system relied on pressed steel drums, a cost-saving measure that did not stand up to repeated heavy use. As the brakes heated up during long runs or while towing loads downhill, the steel drums expanded. Operators would press the pedal and feel normal resistance, but the stopping force would fade away just when it was needed most. Stories circulated of tractors running away on hills, unable to slow down despite frantic braking. Dealer mechanics scrambled to address the issue, and by 1955, Allis-Chalmers switched to cast-iron brake drums in new production. The change was quietly recorded in service updates, and field repairs became a regular job for local shops. Today, WD45 restorers know to check for the cast-iron upgrade before taking a machine out on a slope. Thermal expansion in braking systems is now a standard topic in agricultural engineering classes, a direct legacy of the WD45's early misstep. Both the 1066 and the WD45 reveal how comfort and material choices, made with the best intentions, can have hidden costs. Dealer bulletins, hurried redesigns, and operator complaints all tell the same story. Even small details like the route of an air vent or the composition of a brake drum can tip the balance between safety and hazard. The lessons learned from these machines echo through every new tractor design, reminding engineers and farmers alike that progress sometimes comes with surprises no one wanted. The Ford 5000 arrived in the mid-1960s with a promise of safety and modern engineering. Advertisements touted its split brake system, allowing independent left and right control for sharper turns and better maneuvering. Underneath, though, the design relied on a cast-iron linkage to connect the brake pedals to the rear axle assemblies. This component, meant to bear the full force of emergency stops and heavy fieldwork, faced stresses its designers had not fully anticipated. Over time, cracks began to appear, sometimes without warning, sometimes after years of hard use. When the linkage failed, both brakes could suddenly give way. Operators described the sensation as pressing on air. No resistance, no stopping power, just a rolling machine and a rising sense of panic. Service bulletins started circulating by 1968, urging dealers to inspect for stress fractures and replace suspect parts. By 1971, Ford authorized a retrofit using a hardened steel linkage, and later models quietly adopted the upgrade. Restoration mechanics still find broken originals in barn finds today. As one veteran mechanic put it, if you see a Ford 5000 with the old cast iron linkage, you swap it out before you even think about starting the engine. Another surprise lurked at the back of the tractor. The live PTO, a selling point for its convenience, kept spinning even when the tractor stopped moving. Implements could lurch or spin unexpectedly, catching operators off guard. Ford's later service campaigns added PTO guards and clearer warning labels, but the early years saw more than a few close calls. The Ford 5000 story is a reminder that even well-intentioned safety features can hide their own risks. Sometimes it is the parts you trust most that let you down. Hydraulic pressure can turn a minor flaw into a dramatic hazard. On the John Deere 4020, the high-pressure system powered heavy implements with ease, but early hoses were not up to the task. In the early 1970s, dealers received urgent bulletins. Field failures were sending jets of hot hydraulic fluid spraying unpredictably when a hose ruptured under load. These were not slow leaks. Operators described a sudden hiss, then a stinging spray across hands or arms. Lawsuits and insurance claims followed. Deere responded by upgrading hose specifications and labeling pressure ratings on replacements. By 1975, mechanics were trained to inspect hoses on every service call, and dealers kept replacement kits on hand. Today's hydraulic systems carry warning stickers and colored tags. This is a direct result of those high-pressure lessons. The physics behind tractor safety is not always visible, but it can be just as unforgiving. The Ford 9N, 2N, and 8N series brought the three-point hitch to American farms in 1939, promising unmatched versatility. Buried in a stack of internal memos from 1939 to 1941 was a warning. The hitch geometry could send force upward and backward if an implement hit a buried rock or stump. In the field, that meant the rear wheels could lift off the ground and the tractor could tip back in a split second. Those backflip incidents became infamous in farm diaries and extension reports. Only after years of field experience did engineers add stabilizer bars and adjust the geometry to redirect force safely downward. The solution came too late for some, but it set the standard for hitch design and operator training for decades to come. Fluid under pressure and force vectors at the hitch shape the way modern tractors are built and the way safety is taught. The scars left by hose ruptures and sudden tip-overs are reminders that even the smallest design details can have outsized consequences in the real world. Every year, over 130,000 farm injuries in the US involve machinery, proof that engineering choices still shape real lives. As technology races ahead, the line between innovation and risk remains razor-thin. Today's safety standards are written in lessons learned the hard way. The next breakthrough could be tomorrow's regret or tomorrow's salvation. Progress demands vigilance because in farming, design is never just about machines. It's about trust and survival.